So last time we saw the proof of the following lemma. Gamma be a leveling function from 1 to q. Is a polynomial. Polynomial time algorithm which finds a set Pg of size Okay. So what we showed last time that if I have an interval graph and you're given a labeling function, then I can basically find an universal epsilon universal labeling independent set covering family of G of not too large size. And today what I want to show to you is at least a couple of application of this. So one problem which has been quite central in parameterized complexity kernelization lower bound is called disjoint factors. So let me first define what is disjoint factors are and what is this. So suppose you are given a string, okay. So now what are factors? So this is called factor. So between you have a string or substring, you have a substring starting and ending at the same letter, okay. So this is called factor. We also call it, if suppose this is A and A, we also call it A factor. Okay. Now what does the disjoint factor problem ask? So your input is, so at least the disjoint version which has been studied in literature is that input is some x in sigma star, sigma is some fixed alphabet, parameter is size of sigma, and the question is, does x has disjoint factor? Okay. Now I will define what I mean by disjoint factors. So what basically they wanted is the following. So for example, what I mean by disjoint factor. So now here is a disjoint factor and starting and ending at the same letter, and this is non-trivial in the sense that it cannot be that you have a one letter alphabet, like this is not a factor, right. So by definition a factor has size and the same letter, substring starting and ending, let us call it of size greater or equal to 2 and ending in the same letter, okay. Now what are disjoint factors? So okay, so by disjoint factor we mean a set of strings, set of substrings or set of substrings that are pairwise disjoint, or let's call it disjoint factor is like, okay, let epsilon prime be subset of epsilon, then epsilon prime disjoint factor is set of substrings or set of factors for each letter in sigma star, for each letter in sigma prime, and they are pairwise disjoint. So in other words, so suppose I'll call it, this is factor. So basically you have some x, okay, let's call it x, y delta in prime, y delta is a delta factor, and for any delta 1 delta 2 in sigma prime, y delta 1 intersection y delta 2 is phi. So they do not even overlap. Okay. So for example, what are the factors here? So here, suppose here we have 3 letters. So how many does it has a factors corresponding to, say, factors corresponding to sigma, right? So what they meant in disjoint factors, does x has a disjoint factor with respect to sigma, like everybody should be covered, okay, and that was the whole motivation. Now, okay,
it means somehow, okay, for every letter in sigma there should be a disjoint factor. There should be one factor and those factors have to be a disjoint, something like that.
Yes, that's the definition, right? Okay. So now, does this string has a factor corresponding to sigma?
A, B, C, these 3 are the say alphabets, then no, this doesn't track, because only 2 you can get somehow.
Look, for A, either I need to pick this,
yes, or say just two consecutive,
right, and then or I can pick this.
If you pick this, then you can pick only one.
Either way, so it does not have a disjoint factor.
2 at most you can have, but not 3.
Yes. So this example does not have factors corresponding to sigma. Now, if you notice, so this was shown that, so they studied this decision version of the problem. Now, what they showed that disjoint factor has no polynomial kernel. And from here you can show that cycle packing does not have a polynomial kernel. How? So suppose I will give a polynomial time, a PPT reduction from disjoint factor to cycle packing. And what is cycle packing? So input is g comma k, parameter is k, and the question is that G has k vertex disjoint cycles. Okay, the G has k vertex disjoint cycles. Okay. 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 Fine. Okay. And now, how do you give reduction from here? So suppose I knew that I have such an object. So basically, if I have a letter x, right, and I have given an input given an input string x over sigma. So suppose your x is like a b a b a b a c c d a b c d a b c some. So what you do is that you create a vertex for each letter in sigma, okay, a vertex for each letter in sigma, okay. So suppose we have a b c d here, so like this is a, this is b, this is c, we don't have any more, no, we also had some, no, we don't have d, okay. So now what you do, you think of this x as a path, okay, so with vertex labeled with a b a b, so this is, think of them as a path, not as a string. So maybe this is like a b a b a b, okay, like this, okay. Now what I do, I make a adjacent to all the a's, and so on, okay. Now I will make b adjacent to all the b, okay. I make c adjacent to all the c guys. So c comes here, c comes here, c comes here, c comes here, and then finally I make d adjacent to all the letters starting with d. So for example here, do we see more d's here, d, right? So this is your construction, that's end of it, okay. Now notice if, so now what we have to show, that if x has factor or disjoint factor corresponding to sigma, if and only if g prime sigma is a yes instance, g prime sigma has mod sigma vertex disjoint cycles, okay, that's what we have to show. Now forward direction is obvious, right? I mean, look, if I have a disjoint factor, then in this string they are disjoint, they do not overlap. So basically I will get, what will I get? I will get something starting like this, something like this, something like this, something like this, right? If I have a disjoint factor, what is the meaning of this? These are the strings who do not overlap and they start and end at the same letter, right? So now how will I get? So okay, I look at the first letter and the last letter, and I know that there is an edges going up, so I, right, whatever this guy is, I just go and take this, right? So this will give you basically a path, and you take this vertex and the cycle. Take this path, take the corresponding endpoint, and look at it. This is how we have given edges. So this will prove the forward direction. If I have an x disjoint factor corresponding to sigma, then I have so many vertex disjoint cycle, right? Now if you have any vertex disjoint cycle, how can a vertex disjoint cycle be? Okay, how can a vertex disjoint cycle look like? Now notice, if I delete all these vertices, then if I delete all these vertices, then there is no cycle. But there is absolutely no cycle, this is just a path, right? But how many letters, how many these special vertices we have? Let's call them special vertices. So for the reverse direction, there are cardinality sigma special vertices, right? And if we have say mod sigma vertex disjoint cycles, then I am going to call them C delta in sigma. Why? Because for each vertex, I know that every cycle must take one vertex and I have exactly this much. So I just call them by that name, C delta, delta and sigma. Now what is the property of these cycles? They are vertex adjoint cycles. So if I start from here, look at its end point here, right? Its end point here, right? It just goes and ends somewhere and goes back again, right? There is no way, it could also be, what happens? Why not it can go here and come back and then do this? Well, if it does this, then the B is already used. If any two cycles will use this B or this C or this T, then we are dead. So any cycle looks like in this graph, I start from A, look at any cycle C delta, we have a cycle for every vertex here. It means no cycle is going to use one of the top special vertices. If no one is going to use any top special vertices, then A comes from, a cycle from A will come to A, it traverses a path and goes back. B comes back, traverses a path and goes back, and they cannot overlap, because if they overlap then they are not vertex adjoint, right? This implies that you look at your cycle C delta, look at its projection. Now project C delta to, let's call this path Px, to path Px, and you get your disjoint factors, right? So what does this instance tells us, right? This instance tells us that if at all there are hard instances of cycle packing, I mean there could be more, but definitely if we are trying to make a polynomial, so what, even on these kind of instances, which is nothing but path and some set of vertices, cycle packing does not have a polynomial kernel. So a natural strategy will be, is it possible for us that we do some polynomial time kernelization procedure and boil down to these kind of instances, and once we have boiled down to these kind of instances, let's see how we can handle it and get a lossy kernel for these problems, okay? And that is the whole ball game for this. So to give you this reduction is just to tell you that hardness tells us that, okay, if I am trying to do anything, if I am trying to find something simpler or lossy kernel or something for this, I first must understand how does it happen on the hard instances. They are my hard instances, this is what I have created, right? So path plus some vertices which are flying around everywhere, right? Can I deal with them? So this is how you think, this is how you design your algorithm, by looking at your NP hardness reduction or hardness of any form, okay? So first let me give you a straightforward, so first forget about that. I mean if I am trying to capture this setup, there is much simpler thing which does not have a polykernel, is disjoint factor itself, right? Just with path, and I want to capture this, because that is from where the hardness comes, because this is a polynomial parameter preserving reduction. So if I can get a certain kind of good objects for this, then this transformation will allow us to maybe to transfer the same thing for this, right? So it makes much more sense for me to first try to understand that whether I can get a whatever good object I would like to create from the start for the starting problem. This is why when you give a reduction from SAT to something, right, you basically say, well, there is no point putting your effort on the other side of the problem, but go try to design a good algorithm for SAT, because that is much more basic and fundamental, and what you have shown is your problem is maybe more difficult than what you started with. Okay, fine. So what I am going to do is to give you a lossy kernel for disjoint factor. Okay, lossy kernel for disjoint factor using this lemma, and outline you, if I have a time, I will outline you how do we get to cycle packing polykernel, lossy kernel. Okay, fine. Okay, but this is a decision problem. Okay, this is a decision problem, right? So what will be an optimization question? The optimization question will be, I would like to pack as many letters of sigma as I can, right? The maximization version of this problem will be, I would like to pack as many letters of sigma as I can, right? For example, satisfiability, what is the decision version of question? I want to satisfy as many clauses as possible, right? So similarly here, I would like to pack as many letters of sigma as I can, okay? and again with respect to disjoint. So I would like to find a sigma prime for which I can get a disjoint factor, and I would like the size of sigma prime to be as large as possible. Okay. Now, so this leads to, if you recall correctly, okay. So if you remember the definition of optimization problem, what was this? Pi was a function from sigma star cross natural number times sigma star to reals, right? What is the meaning of this? It was that, okay, pi first 2 is basically a tuple, parameterized complexity tuple, okay. So for example, x k input and a parameter, and what was y? Y was a certificate, right? Y was a certificate of, or think of this, y was like a solution, right? So what does pi maps to? Given an instance x comma k and a string y, which I think solution, what is its value? Like what does its value is, right? The way an optimization problem is defined. And now what did we define? So let's call this instance I, right? So we had a natural definition of what is an optimization, what is an optimization, or what is a minimization or maximization problem is. So given x comma k, what did we say? Well, look, for the same instance x comma k, I could have many strings y. So for example, if you have a graph, there are many vertex covers, right? But there are only few vertex cover of the smallest size or something. So we had this notion of optimum. So how did we define optimum? Okay. So for convenience, we added plus minus infinity to mean. Okay. So optimum value of an instance we defined as opt pi, right? And let's call it I comma k, doesn't matter. Some instance comma k was nothing but, so I'm only defining for min, you can define for the, so let me define for max, because that is what we are using. Max s element of sigma star. I am not allowing certificate to be unbounded for certain feasibility reason. So I can take here polynomial in I, or it does not matter, right? So what is an opt of an instance for a parameterized problem pi is basically I go over all string or go over all solution and I choose the one for which this pi value is maximized, right? And what is an optimal solution? An optimal solution S is what? Pi I k S is nothing but opt pi I comma k, right? So S is called an optimum solution if I look at the value of pi on that, it is same as opt, right? So this is how we define an optimization problem, and I'm not going to go more into details. So now to make sense of this, we need to define an optimization version of disjoint factor. Okay, so what is an optimization function? So I have to define an function from sigma star cross natural number times sigma star to, okay. So how do I define this? So what is an input to disjoint factor? The input to a disjoint factor is a string, right? And what is k? K is basically the size of this alphabet. Okay. So why I write f disjoint factor? So basically the function is I take L string over alphabet sigma, which is my parameter, and some set S, where S is set of strings, substrings, and this is equal to minus infinity if S is not a set of disjoint factors of L. Meaning you gave me some malformed solution, maybe they are overlapping, right? In that case I map it to minus infinity. That is by choice. I'm not interested at this point of time looking at any feasible solution, right? I'm trying to restrict the feasibility reason, which is okay for most natural problems, without worrying about anything else. If I allow this to be unbounded, I do not want my domain where I'm trying to maximize or minimize to be unbounded. So I'm only interested in those solutions which is not too large. This is my choice. You can make it poly or this, the definition will hold. It depends, it can be, right? It depends on what encoding we use, like numbers and this, right? So this is a bit delicate, okay? It can be, I mean, let's put it this way, it can be, right? And yeah, it can be very large, okay? It depends on I can define such a problem. I can define an unnatural problem for which the solution by definition is something huge than the instance, right? I mean, that's like that string which is a solution, so-called solution or something, it's very huge. For example, I can write in a very succinct way 2 power n is nothing but, okay, it is log n where power has been taken to the power, like it has been taken 2. So it's a very succinct representation of something which is too huge, right? So no, the string which I'm interested in is huge, but I may not be able to see it, I may not be able to show it, right? So it's just that I want to have only feasible range. This is, I mean, why can't I have a polynomial length strings in input as a solution? Why can't a solution be not a polynomial length? Because why a solution always have to be subset of this or something of this? No, maybe looking at input I will create something. For example, I'll give you region, I'll give you very simple example. My problem is I give you integer n. How many bits does it require? Log n. Output all the numbers, and what is my input is this, and output all the numbers from 1 to n.
Input is just a number.
And output is you output all the numbers from 1 to that number. So I gave you 10 n. How many bits does it require? Log n bits, right? But if I have to return you all the 1 to n, how many bits do I require? So it is exponentially larger, or it is polynomially larger.
For every number you need.
So my solution, yes, so it is larger than the input, right?
Yeah, but then I plus k, this is larger than I plus k as well.
Of course it is larger than I plus k, right? I am just giving you an example that you said that for which problem you can have. Yes, there can be many problems, and I could also write poly in I plus k here, right? Right. So for example, if I say I have log n, you output all the numbers from power up to 2 power log n. Now I have exponential. So all I am trying to do is that I am only trying to capture things which is very natural, set of problems which I am trying to capture by the framework, and for that it is good enough for me that I restrict myself to the solutions which are not too large, or the solution strings which are not too large. That allows me to have a bound on the feasible region where I am looking for a solution, and that is it, right. This itself means, what are you looking for? You are looking for a solution space has size 2 to the power mod I plus k, you are looking like that large. So I am allowing myself to be that large. If I put 2 times poly I plus k, then I am allowing that to be large, and it would not matter much for this formulation to go through if you put poly I plus k here. I mean, it would not make much difference, like everything would go through. Okay. So now what is this function? It takes my string, parameter is the size of the alphabet, and here is the size of some set of substrings, okay, and it is minus infinity if S is not set of disjoint factors of L. I mean, they are overlapping, or their first letter and the last letter does not match, it could be anything. So if it is malformed in whatever sense it is, then this is, else what you return? Size of this, right? And since it's a disjoint, it's a set, right? It's a set of disjoint factors. So you're not returning, you're not giving me for the same letter too. It doesn't matter to me. I'm not interested in those answers. I'll just delete it and just keep one, right? So for every letter, I only have one string in my set. Okay. So this is my function, and this is what we would like to optimize over, right? So now what I'm going to give you? I'm going to give you okay, I'm going to give you a lossy kernel for this. So what I mean by lossy kernel, I'm going to give you an input is going to be L sigma, right, and I'm going to output some L prime, the input is over sigma, and the parameter is sigma. I'm going to give you another string L prime, okay, which have some relation of this, and what will be, maybe it will be over sigma, it does not matter, and the parameter is still the length of this. Now what is the property we would like to have? We would like to have two algorithms. One is called, we call what, reduction algorithm, right? So we have two algorithms. Okay. Okay. So one is called reduction algorithm. What does it does? So basically it is, reduction algorithm is sigma cross natural number, it returns you some another sigma cross natural number, right? So given an instance, it returns another instance, okay? I'm not talking about equivalence, non-equivalence, nothing. It just returns an instance like this. This is what it does, okay? It does nothing more. Okay. So in parameterized complexity language, what would it be? We call it I, K, where L and sigma is part of this, and I have returned you some I prime, K prime, right? But for us, K prime will be sigma in our C. But next is what is called solution lifting algorithm. What is a solution lifting algorithm? It tells me that if you give me a, so it takes as input, it takes, what does it has? It takes as input I comma k, it takes as input I prime k prime, and it takes what? A solution for this, okay? Okay, it takes some S prime, a solution to I prime k prime, and what does it does? It returns you a solution to
I comma k.
okay, and works polynomial in all the above and outputs a solution S to I comma k. This is what it does. Okay, so this is what it does. So it's a two. So what is this? We have two algorithms. One which reduces the instance, and another which outputs me a solution given an input instance, output instance, and a solution to the problem. So we need to design these two algorithms. Now, how good or bad it is, now we will quantify it. That okay, what did we achieve by this reduction? We need to quantify this. Okay. Okay. Okay, so what should I rub? So you have understood this question. I'll remove this. Okay, and we say that our pair of reduction and solution lifting algorithms for pi is an alpha approximate polynomial time preprocessing algorithm if what happens. So like I have not talked about size or anything, all I am saying that I am defining a notion of alpha approximate polynomial time preprocessing algorithm, right. So we will worry about the size. So it has two algorithms, one is reduction algorithm, another is solution lifting algorithm. Reduction algorithm just returns you an instance of the same problem if it is kernelization algorithm, right. And if you have just talked about compression, then this could be another language also, right. So this is something which you still have to maintain, right. So I cannot give you if I say that I have alpha approximate kernelization algorithm, not polynomial time preprocessing algorithm, right. If I say I have an alpha approximate kernelization algorithm, or then the output instance must be of the same language, but I could also define a compression and then it could be a different language. So, but now first let us see what property do we want. So, if pi is minimization problem, then what do we want? That well, pi of I comma k comma s. So I gave him a solution, right. My solution lifting algorithm gave him a solution S. The quality of this solution, right, I will forget, I mean ideally I should write opt pi I k. So the quality of these two solution, like quality of optimum to what you have returned is at most alpha worse than and look here I have defined it with respect to the same problem, but if it would have been say pi and it would have been some other language we would have been mapping to, then we have to define things accordingly, okay. But let us not get into this. Now what does it tells us? That look, if you give me an exact solution here, somehow you have been able to solve exact, this is 1, all I am guaranteeing to you that whatever solution I will return you is alpha away from the optimum in that instance. If you give me a factor 2 approximation here for the reduced instance, that solution, if S prime is a factor 2 approximation in this sense, then I can only guarantee you factor 2 alpha approximation for the original instance, right. My solution S is definitely guaranteed to be a factor 2 approximation there, okay. What? In all my description up until now, I am only talking with respect to one problem. Pi is one optimization problem, okay. I could also have two different problems, pi and pi prime or pi star, and what does my reduction algorithm does? It takes an instance of pi, produces an instance of pi prime, right. Now if I had a pi prime, then how should I define? I should define pi prime and opt of pi prime, because it's a so if that is a factor blah approximation, that will translate into that alpha times that approximation for the original instance, right. That's all that I'm saying, but we'll stick to the same problem for now, okay. So this is what it means to be okay. So now what I'm going to do, I'm going to give you these two algorithms with the following property, okay. So what you will give me, okay, so I'm going to give you basically like a 1 plus epsilon approximation, okay. So what I mean by, and okay, and another thing is important all the time is that alpha for all our discussion is greater than equal to 1. Let alpha be a real number, okay. This is how whole, you can define it with not also. So this is for the minimization problem, and if pi is a maximization problem, what do you expect? Pi I k s divided by opt pi I comma k. What do you think? Greater than equal to? So greater than equal to 1 by alpha. So which is same as saying that this is this time the alpha is pi I prime k prime s prime divided by opt pi I prime k prime. That's it, right? Because alpha is greater than 1.
What happens when
Say max cut. Think. Max cut is an optimization problem, right?
what happens when pi and pi? Pi is maximization problem and pi prime is a minimization problem.
Nothing will happen. You have to just translate them appropriately.
So the factors and ratios, they still get multiplied.
It will exactly same multiply, because it's with respect to pi. How worse the pi is with respect to the solution you provided, right? So you gave me a solution, right? How worse I am with respect to your worse, right? Right? Alpha is like the loss which I allow you to.
For example, if pi is a minimization problem,
Yes. Forget for now. Suppose alpha is 1. What with, and pi is the minimization problem. What does it mean? That look, the approximation guarantee on output solution is at least as good as an approximation guarantee of reduced instance. Right? This is what this says. What is this is ratio.
yes. So if so look at the first inequality,
Hmm?
first one. So if pi is a minimization problem, this is what is supposed to hold.
Which one?
The first one. If pi is a minimization problem,
Mm-hmm.
right? Now the right hand side of the inequality is pi prime.
Yes.
Now pi prime by opt of pi prime is say 1 by 2. Now pi prime is a maximization problem.
Okay.
So it will have some fraction. This value will be some fraction, right?
It should be.
So now suppose your alpha was 2 and this was a maximization problem which was giving you a half guarantee.
Mhm.
If you use this inequality, it actually means it's giving you the correct answer, because alpha
No,
is 2
wait.
and half will get cancelled.
No. Wait. Okay, fine. What does it mean? Let's try to understand, right? So suppose, what is an alpha? Alpha is greater than 1, right? So if it is a maximization problem also, right, how are you going to what is that called? Let me think.
Ratio for both the kinds of problems we can define it to be greater than or equal to 1.
No, I mean, so for maximization problem, you'll write the reverse of.
Well, I'm saying don't write. I assume that the approximation factor is always greater than or equal to 1 for minimization and maximization.
Yeah, for that you'll have to write the right hand side of the first equation is the reverse things.
Yes. Okay, for the compression we need to think. Okay, what will happen? I cannot think offhand. Okay, so I'll tell you. So for now, both are of the same kind. Anyway, my pi's are same, so both are maximization problem. You're right. I mean, it requires bit of arm twisting to fix which inequality should go where. I mean, if both pi and pi prime are different nature, then maybe we need to do some arm twisting here. Okay, but I mean, I'm pretty sure that should be doable. Okay, fine. So this is what we would like to have. Okay. Now what I'm going to give you without going into the definitions and all this is for disjoint factor, which we defined just now here. Design you these two algorithm with the following property. Okay. So you give me an epsilon greater than 0. So what is the algorithm I'm going to provide to you? So you give me okay. So what I'm going to do is that for every epsilon greater than 0, okay, for every epsilon greater than 0, what I'm going to give you is okay. So what I'm going to give you is an algorithm which is what it will do is that it will give you, so first of all it's a reduction algorithm. So given an instance, say I comma k, where I is basically L and sigma and k is nothing but cardinality of sigma. Okay, I'm going to give you some I prime, k prime, and as I told you, this is going to be L prime, sigma and k. It will have some size bound. First of all, it will have some size bound. And secondly, it will have quality bound. Okay, it will have a quality bound. What is the quality bound? How much I'm going to lose? Okay, so the loss will be controlled by epsilon, right? So what I will give you is that, well, if you give me a solution here S, okay, I will output a say S prime here, I will output a solution S with the following property, that the size of S is going to be at least 1 minus epsilon times size of S, right, size of S. Okay, this is all that I'll guarantee you. Okay, now no, I don't think I'm going to guarantee you. Okay, no, I'm going to guarantee you is that the S which you will give me is whatever you will return me, okay, whatever you will return me from here to here, okay, is that if whatever maybe its size is, I'm going to return you S exactly equal to size of S prime. Now, what did I say? That if you give me S prime of length 10, I will return you a solution of length 10 in the original graph. Now, that does not mean that I have not lost something, right? What I mean by I have not lost something, that when I went for the reduction, what happened is that there itself I will tell you that look, whatever you started with an opt here, what you went new opt here is already I have lost by fraction. So even if you give me an exact solution there, right, I will not be able to return too much to the original instance, okay. So you should understand what I am trying to say. What I am saying that in the reduction algorithm, I cannot guarantee you that opt has not shrunk, right, opt could decrease, right, but what I am saying, whatever size you give me an object here, whatever size object you give me here, I will give you exact size object here, right, but I cannot, that does not mean that if I have a k size solution here, look, so for example, how do we prove normal kernelage? Well, if I have a k size solution here, I have a k size solution here, right. So this is why I'm still, we have to write what this is, okay. Now what will happen in the forward direction, we can say, hey, if I have a k size solution, I can only guarantee you that my algorithm, like I can only guarantee you a certain kind of solution for the certain kind of solutions only exist in the output instance, okay, and hence even if you solve it optimally, I cannot guarantee you that you will give me an exact solution here, right. What generally happens in kernelization, if you solve me exactly, I will definitely give you an exact solution here for the original instance, okay, but this guarantee I will not give you, okay. So this is what is going to happen. You will see more clearly what the statements are. Right, and you will see how these things happens, okay. Okay, fine. Okay. So let's see, and then we'll figure out everything on the fly, okay. It's not something very, like, given that lemma, everything is actually trivial, okay. So you have given me some epsilon, and I would like to at least return you a solution of quality, say 1 minus epsilon. So what I would like to have is the following thing, okay. I would like to prove to you that if you gave me an epsilon greater than 0, then I will do something to my instance with the property. Let's look at this here, because that will give us some idea of what we would like to achieve. So disjoint factor I comma k and s, whatever it is returning, okay. Yes, that's a value, times opt of L sigma is at least 1 minus epsilon times, okay, 1 minus epsilon times S prime opt I, or I'm going to give what, L prime S prime. Now you notice this is 1 minus epsilon, epsilon is greater than 0, so this is something less than 1. So when I bring it here, it will become greater than 1. This is something less than 1, right. So when I bring it this side, whatever it is, by dividing it by, how can I do it, divide it by 1 minus epsilon both sides, right. This becomes 1 and you get 1 by 1 minus epsilon, 1 minus epsilon is less than 1, so 1 by 1 minus epsilon is something more than 1, fine, okay. So this is my goal. What I want to achieve is basically this, okay. Now rather than defining terminology for you, okay, let's see what naturally things we would do. Look, I have a string, right, I have a string and I'm happy to lose some factors, right? What is my goal? I have string, right? So what I'm going to do, so suppose here is my string, okay, indexed by letters in sigma. This is what I have, right? So if at all I would like to utilize this, right, I need to have two things in my head. First of all, I need to create an interval graph from here, need to interpret every disjoint factor as a independent set in my this graph, because solution should correspond to independent set. And then what we would like to do, once we have interpreted these two things properly here, we would like to apply this lemma and say, hey, then there are only small set of letters which is useful, like it will tell us, right, then okay, take this x which is close to all independent sets. So what we would like to have, every disjoint factor, optimal or non-optimal with respect to any sigma prime, should correspond to an independent set in my interval graph. Okay, so if I would like to apply this lemma to shrunk this, what is my objective? My objective is, we'll say, hey, look, it will tell me that for a good approximation of all the independent sets here, it is good enough for you to take this set of letters, right? Take this set of letters, or take this set of positions. Basically, it will tell me positions, right? Because I'm going to create a graph, so it will tell me a vertex set which will correspond to the positions in my letter. And we'll say, okay, fine, if these are the only position which I have to worry about, let's forget about all the letters in between. So you just shrunk, right? So you just forget those substrings, those letters which do not appear in that set. So it will tell us that, okay, pick this, pick this, pick this, pick this. Then what will we do? We'll say, okay, let's consider another L prime which consists of this, forget these letters, take the next yellow letter, forget this letter, take the next letter, forget all this, take the next letter, forget all this and take. So whatever it will tell us, we will do that. And then we will prove all the maths. I mean, let's not get ourselves completely confused with maths and we do not understand the why and what it is coming. Okay, so now what is a natural notion of interval graph here, and what is a natural notion of independence that the disjoint factor is completely captured here? It's like literally this is a two-line application. Yes, but you have to, that's great that everyone, all of you are right. So just to have a complete clear, let's do one example, okay? Please remember this definition, they are not useful. I mean, like they are just, I wanted to define it, so I defined it. But let's do one concrete example and then we'll see. So let's give me some string L, okay, of alphabet, say A, B, C, D, not more than that, otherwise they will be dark. Okay, but give me sufficiently large. Tell me some string, some letter. What? Yeah, this is what you're allowed to use.
So A, B, C, A, B, B, E, A, C, C, then another D, A, then C, B, then D, double C.
One more letter is allowed. B. So let's first understand that if I had a disjoint factors, if I had a solution, say consisting of, say this here, okay, and then say this here, and then say this here, sorry, previously. Then notice one thing. Okay, I would like to make such kind of thing, but notice one thing, if I have such a solution, then look at A, there's another A here. You're taking all these guys, right, in your solution. So rather, I also can take a solution, I mean like this, so that I allow potentially to more factor to create. For example, then BB got created, right? Right? So you always like to have a minimal in the sense that between, so I would like to actually allow to have a notion of minimal strings, minimal X factor. So what is a minimal A factor? So let's define the notion.
Somehow two consecutive strings is not a very good idea. Those might be get rid of easily.
Yes. So what is a minimal S? What is a minimal A factor? It is a substring between, say, position I less than j such that for all j prime strictly between I and j, okay, let's call it, I'm going to call it L j prime is not equal to A and L of I, think of them as an array, is equal to A. Then I am going to call this as a minimal A factor, right? Nothing in between is A. These are the only two guards. So if there is an optimum solution, then there is an optimum solution containing minimal solutions, right? So this will actually allow us to get away certain amount of redundancy. Okay, fine. So from now onwards we will be only interested in minimal disjoint factor, because there is utter waste, right, of using the same letter in between. So then I can just take something shorter and I still am good. Okay, so now if I have told you, so what is the natural notion of this thing? So what I will do, I will make an interval for every minimal strings. Okay, if I have to, so what is this? This is a very simple interval graph. I go from, look at all the position of A. These are the only position of A's, okay. So you make, so I will make yellow for A. So I will just make A and then next consecutive two A's, so they will overlap here, and then A and then A, okay. This is what it is. Now if there is an optimum solution for A, there is one which takes one of these guys, right? Takes one of these guys. If there is an optimal solution where A factor, then I can create the one which consists of one of these guys. Now let's do it for B, right? So where is B? B is here, B is here, B is here. Where is else is B? Here. Okay, so let's use them. Okay, so we will have a bad time here, but let's look at this. B, 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 and then another B from here to here, and another B from here to here, right? I'm making, this is how you make your interval graph, right? I'm not, okay, now let's say C. So where is C? C is here, 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 C is here. Okay, fine. So I start from here and I need to go here, right? So C, then another C, and C, C, okay, another C, C, okay, C. Now let's look at D. Where is D? First time I see occurring here, then I see occurring here, and then I see occurring here. Is it true? Okay, so start from here. D, D, is it correct? Yeah, yeah, there are only two of them. Okay, now tell me, question number 1. Okay, so this is my interval graph which I am trying to consider. Now so claim, let S be a set of disjoint factors. Let S be set of disjoint, minimal disjoint factors, okay. So only consisting of minimal thing, minimal string. Then corresponding intervals of S in, let's call this interval graph L interval, okay, in L interval forms an independent set, right. Look, it is a minimal thing, right, and they are disjoint, so they cannot overlap, right. And so first, any minimal guy is captured as an interval. First let us just understand that any minimal object is captured as an interval by our choice of intervals, and now by choice, by definition, they are disjoint factors, right. So they are not overlapping. So how can as an interval they can overlap, right. So clearly any minimal solution forms an independent set here, and every independent set here which is colorful will give you a set of disjoint factors, because it can happen, look, this and this are the same factor, right. So it is not that, this is what I am saying, it is not that every independent set here will correspond to that many disjoint factors, but every disjoint factors definitely corresponds to an independent set. So this guy has far more independent sets than what we want, right. So I cannot give a bijective correspondence between, well, because why I can't give, think about it, right. Why I can't give, because what I am looking for is colorful independent set here, and maybe colorful independent set on interval graph is NP complete, because if all we were interested in find a maximum independent set, then on interval graph we can find this in polynomial time, right. But you are not guaranteed that it will give me different colors. So basically this is not a problem on normal interval graph, this is a problem on a colored interval graph, right. So you have a family of intervals, so you can partition your intervals on different family of colors, and basically you would like to find an independent set which touches as many colors as possible, right. So this is where it becomes a colorful independent set, not independent set, otherwise we could have solved this problem in polynomial time, okay. Now that we have captured all these notions, fine. Now, so we have made our interval graph, right, we have made our labeling, right. What is labeling? Vg to Q, right. So I label each interval with a letter, right. So what I do, so what are these guys? They are labeled with A. What are these labeled with? B, right. So I automatically, sorry, C, and this is D. So I have automatically defined, like I have a natural, the way I have defined my interval graph, I have a natural labeling this, right. Now to be useful for our purpose, we have to bound, this is, so what is Q? So what is the Q in our setting? Is bounded by sigma, which is our parameter, so we are very happy. But now somehow we have to bind the chromatic number of this graph, right. We have to bound the chromatic number of this graph. What is the chromatic number of this graph is? What is chi of L interval, right? If it is not a function of sigma, then that is not part of our parameter, right? So what is a chromatic number? What is a chromatic number of interval graph? It is same as a clique number of the interval graph, because in any perfect graph, size of clique, maximum size of clique is same as the chromatic number of the graph. So what is the maximum size of a clique here? So to prove a maximum size of clique, you just pick at any point and see how many intervals are going through it. So if I pick at a point, how many intervals can go through? At most, if I pick at any point, it is possible that for every sigma, at most 2 intervals are intersecting. For example, here, it is possible that maybe all the guys but something, right? I mean, one can prove much better bound probably. I mean, this will never happen, because at any point of time, because the way the intervals are, it could, is it possible? Yeah, it is possible that maybe I can cross like this. No, that cannot happen. Actually, it is sigma plus 1. But in the worst case, it is sigma. But you will prove sigma plus 1. Okay? That's your duty. Okay? So everything is bounded. So now I will apply this lemma. and I get a set X. What do I get? I get X, set of intervals, right? Okay, now what I'll do, apply lemma. Apply lemma, say star on L int gamma Vj to basically sigma. This is what our function is, right? And what will we get? What will it return us? An X subset of V L int interval. I mean, I'm just using any symbol because to give you a flavor. I mean, right? How do you? So to use this lemma, I need to create an independent graph. I need to create first interval graph. Then I need to define a leveling function. But in more case, this will always happen very naturally. Okay. And then third, you have to bound the chromatic number of this graph as a function of your parameter. So the things you are also allowed to bound as a function of epsilon, right? Because I'm allowing my size to be as big as some function of k comma epsilon. So it could also be function of epsilon, but in general, this is the only freedom you have. It should be bounded by k and epsilon because it's interval graph. So just bound the click size and you're happy. So now we get xvg, which is epsilon u-less in g. So what is my natural thing to do at this point of time? Nothing, but just do one thing. So what are they? It returns me intervals, okay? It returns me intervals. So what I do, I take the both endpoints because that corresponds to letter. Interval corresponds to 2 letters, right? So I just took positions, not letters, took positions. Every interval corresponds to 2 positions. So now the best way to think of L is like every letter has a position involved, right? So think of them as an array, right? Think of this L as an array because if it returns me this guy, I would like to remember this and this, not the letter per se. Letter per se is not important, but the position is important. You return me because that is what corresponds to vertex, right? What does correspond to vertex? Position. So it will tell me, oh, keep the interval between 5 and 7. So then I should remember the 5th position and the 7th position.
Is the position important or just the ordering is important?
Ordering is important, right? But how do I remember ordering? By just knowing the positions, right? So what is the natural thing to do once we have defined this? Okay, is that okay? We will view okay. We view each substring as a positional substring between some index I and j, right? This is just to visualize this, right? So think of this way, I have a string here. So what is the position of A? 1. What is the position of B? 2, 3, 4, 5, 6. So my interval graph has, it's a real number where the intervals are from 1 to some 3, right? So what is this? So this will be interval from 1 and where does it end? 1, 2, 3, 4. It starts from 4 and ends where? 5, 6, 7, 8 and things like that, right? So this is how you visualize each interval as a substring between 2 positions, okay? Because that is what I would like to know. So now what I say, let x tilde is positions of the endpoints of the intervals in X. Yeah, in X. That is what my X tilde is. What is X tilde? I look at each interval in my, whatever my U list has returned, I look at the both endpoint and I keep X tilde. Okay? So now what I would like to say is that, so given L, I would like to produce L prime. And what is L prime? Okay? Just forget all the positions which is not in X tilde. Okay, what is L tilde? Forget all the positions that are not in X tilde. That's it. So if 6, 7, 8 does not appear, so just forget that. It's like, so what I will keep, I'll keep, say if it tells me to keep 1, 4, 8, so then I will forget BC, AA. This is what meaning of forgetting. I will forget BC, so I will keep A. So I only keep, so just take a substring from left to right for which there is an index in your X tilde, which is same, okay? Or alternatively, keep a substring, or I don't think it should be called substring, subsequence, it is a subsequence only on the indexes present in X tilde. That's it. That's all that I am trying to tell you. Okay. Is it clear, Sanjukta? Is the operation clear? You look very confused, so ask. Hmm? X is not an independent set. Then I am like it returns. So then I will look at 1, 3, 4, 5, right? So 3 is part of my index set, right? Yeah. So I just whichever intervals, whichever indexes are there, alternatively keep a subsequence on the indexes present in X tilde, right? So yeah, if 3, 4 came from your X, yes, then you will only forget which is not present here. If 3 is present, you will keep 3, right? That's okay. Okay. So now I need to, so what is my, I have given you what? I have given you, this is a reduction algorithm, right? What is the size of L, what is the size of L tilde? Okay. What is the size of L tilde? What is the size of L tilde? 2 times whatever this comes from here, which is, what is our Q is nothing but sigma, which is our K. So K into another K, it does not matter, some big O we will put here, so maybe put another 2 here, it does not matter. Okay, you look, just for you, K plus 1, is it okay? Okay, and so this is what it is, 2 times this and big O of 1 over epsilon times log 1 over epsilon, right? Because this is, what is the size of X? This is the size of X. Size of X is this, K into K plus 1 times whatever this big O 1 over epsilon, and L tilde we might have kept, we are keeping both endpoints, right? So 2 times that, this is what it is, which is still big O of all this, so we are fine. So I have given you reduction algorithm. This is my reduction algorithm. And what is my solution lifting algorithm? It's trivial. It tells me what will the solution. So L is nothing but, how did you get from L? You have got your L prime by basically forgetting some things. So if it L tilde returned you 1 and 5, just go and look back at 1 and 5 there. Look, L tilde, think of this with a certain indexes has been. So now you do not have 1, you have 1, 3, 5, 9, 11, 13, 15. Now I returned you 1, 9. Go and check 1, 9 there, right? It is definitely going to be a, whatever factor you have, it is going to be the same factor, because here it's the same letter, so there also it's the same letter. In between it could be anything, I don't care. So what will you return? If you give me some S prime, then I will return you an S of what is the size of S prime? S is exactly equal to S prime, right? I am not losing anything in this. So basically whatever solution you will return me, I will return you this. This is what I can achieve, right? So this is my solution lifting algorithm. Solution lifting algorithm, give me a solution, I go back and return you that index. So this is a very simple application of the lemma once we understand what we are trying to do. But now we still have to show this, right? So is the algorithm clear? Algorithm is very simple. I construct a particular interval graph, I construct a particular labeling function, I apply my lemma, it returns me some set of intervals, I take both endpoints of this, project those, basically I project my string on those intervals and I return you that. And that's my kernelization algorithm, right? And I have just put sigma, I don't care about this, right? But now I have to show that this is a good object. I mean, this is something which is interesting and nice. Now, what should I say? Look, first let's prove something interesting about this. So first I want to say that the opt of my input instance, opt, and opt of my output instance are related to each other. So what I want to say, opt of L comma k, L sigma comma k, okay, is not too far away from the opt of L prime. Why? Because that is where we will use the property of our independent set. So let's first prove some nice property of this. So what I'm going to give you, so if you're going to give me S prime here, an output solution, I will give you the same size solution. So let's, like, just to whatever we know, let's write it down. This is correct, right? What is this? This was the value of pi on the output string. And what are my disjoint factor? If I give me this, then I return you this. Of course, it can also give me minus infinite, but assume that I always have a one string, AA, so I will never return you malformed instance. So this is true. Now, I don't know about this, we have to fix these things, right? We have to fix this. So now what I want to show, okay, so this is all fine, this is good. So now let us forget this claim and make another claim. What I want to show to you is a very simple thing, and that should wrap up our proof, is that what I would like to show to you is that opt of L prime, the string which I returned, comma sigma, is at least 1 minus times epsilon times opt of L comma sigma. This is what I would like to show to you. This is good. So what I say, okay, let P be a maximum sized, okay, maximum sized, okay, disjoint factor for maximum size minimal, important, otherwise we will not be able to prove this, minimal disjoint factors of what? L comma sigma. This instance P is this. What is P in my L interval? This implies, okay, this is why the labeling function comes. What is this? Let P be a maximum size this, right? So P is a labeled, right? P is a sized labeled independent set in L int. Is this correct? Right? Because they are independent set in this, right? In fact, they are labeled with different letters, and that is why its kernel type P. P is a mod P sized labeled independent set, or in our word, what will be this? look at the interval corresponding to this, gamma of interval corresponding to P, if I look at the size of that, this is exactly equal to size of P. This is what I want to say, because you have a different string for different, they form an independent set, so you have just picked up this thing and this is what it is. Fine, P is a P limit, okay, let this independent set be X. So what does it, let this independent set be X. Now what does our epsilon u list tells us? What does epsilon u list tells us? Right? What does this tells us? That if I have an independent set, X with certain number of labels, then, no, I shouldn't say X, this is rubbish because I already using S. S also I have used somewhere, so let's not use this, let's call it W, okay. So what is implied? By the property of epsilon u list, there exists W prime such that is contained inside this, like as a label set they are contained inside each other, and what is the size of this? Right, this is the definition of epsilon u list, right. So what we know, so now if this is the case, then look at this interval graph, look at P, with respect to that you get an independent set W, with respect to that there is a W prime by the construction of this, and what is that property? It has this many labels, right, it is an independent set with this many labels. So it means this interval, this L prime has at least that many disjoint factor, right, at least that many disjoint factor. So what we have shown? We have shown this. Now you tell me why this line implies this line. Just 1 second. So does this follow now? Right? I think it follows from there, no? Directly, right? Because once I prove this, this is just like divide by this, so the inequality will change or something, and then I don't know. I mean, after this, some computation, if you once show this, this leads to this, and we are happy, right? So this is it. That's end of it. So as an algorithm, it's not very hard, right? But okay. So cycle packing is nothing but doing the same thing on a steroid. This is basically what it is, on a steroid, right? So what you do, you take a graph, you apply some theorem, then you basically you create polynomially many instances of long path with things seeing around, okay, using all tricks, like you throw Erdos-Posa first, then you throw another reduction rule if there are too many number of leaves, then that will bound you this, and then there is a very beautiful argument which says that not too many people sees everywhere, so like they are very bounded intersection. So now I have this long paths, that's the only thing I am, because once I am able to bound the number of leaves, then I am able to bound the number of degree 3 vertices. So what is unbounded? These degree 2 paths. Now these degree, it's a forest, right, if I remove the feedback vertex set. So now in this degree 2 paths, there is a set which is seeing like this. Now this is exactly like the instances which we created for this, right. So there is something which, now we have to create in a way that, okay, how can cycle, so now if a path is there, how can a cycle can pass through? So now I have really a path, and this is the, every cycle passes through this. Now I can come like this and I can go like this. But I'm looking for a vertex disjoint cycle. So the other guy cannot come and use like this. So he has to always go like this. You understand? This is exactly the instances on which the problem was hard. So what you do, so you basically do polynomial time preprocessing and get rid of all the things on which you can do something, and you end up exactly those instances on which you showed that your problem was hard. You did not have. So like those were the bare bone objects on which. So now you have these bare bone objects. Of course it has an interaction with all over the world, but then you apply one or two more trick, like standard trick in certain sense, and you get down to the real set of instances on which you need to do the like heavy lifting. And what is the heavy lifting? You apply this some 10 times. So you have to create, right? So the one way to create is like, look, so how do you start even creating an interval? So you say, look, this is too small. Any cycle either uses like this, or it uses like this, or it comes like this, some such things you think, and then you create an interval exactly like this. So now this guy could have lots of neighbors here. So all its neighbors are of type what? His type, right? So but this is not what is capturing solution, right? If the solution is captured, it is possible that I come and I use a vertex neighbor of A, and then I go out with a neighbor of B, some other vertex, right? So this interval should have label what? AB, because I come from A, I go around and I go out with B. So what you do is that you start creating interval graph where the intervals are labeled with pairs of vertices in feedback vertex set. To capture that I have come by A, basically this tells us that in the world I have come from A, I am going to go around and go out of B. And you make, so now I don't know which AB you are going to pick, okay? Like which A is going to come and which B you are going to do. So what you do, you make an interval graph for every pair separately. So I said for pair AB, let's make an interval graph. Okay, so you say like minimal AB, A, B, then A, B, and you do it for BA also. So you made one interval graph, you find some set of objects. Now you do it for another BC pair. So and then you take the union of all those. It's like, but the size of the top guy is like some poly K. So how many interval graphs you're going to create? Poly K interval graphs. Fine. So you have kept some poly K into these many objects. Now how many paths are there? Some really poly K paths. So I have done all this on all of them, and then I get my kernel. But so the harder part is, or the first part of the algorithm is coming up with a decomposition which brings us to those instances, and then how do we visualize these instances as one of these objects, and then apply them, and then you get it, okay? If I feel like I will teach you that, else I would request you to read it. Now it should be very easy to read. I mean, reduction rules are more like feedback vertex set reduction rule, and then the application where you're going to apply is, I wouldn't say it is as obvious as this, but it is not too hard than this. If you like, in my opinion, like just read the first part, do not read the proof of theorem, like wait till you get the decomposition lemma, and then apply yours, then please spend 6 hours if that required to prove the theorem all by yourself. How will you create an instance of that? How will you, like, this is it. It is something which is doable. It is something which is givable as a homework. If I prove the decomposition that, okay, do this, then you get this set of instances, and or the paths with a beautiful property, then how do you go about it? Okay, with this, I'm done. Okay, we will see what we will learn next on the Friday. Okay, bye.